All right, we're here in Algebra 2, lesson 67. This lesson is called Finding Inverse Trigonomic Functions. We've talked about trigonomic functions up to this point. The trigonomic functions that you guys are more familiar with are sine, cosine, and tangent. And so just as a brief run through, what is sine? It is something over something. What is it? No. Opposite over hypotenuse. All right, so SOH, opposite over hypotenuse. What is cosine? Adjacent over hypotenuse. And what is tangent? Opposite over adjacent. So, SOH, CA, CAH, TOA, TOA. So we're talking about finding inverse trigonomic functions. Okay, inverse trigonomic functions. And if you look at your graphing calculator actually has inverse trigonomic functions. If you look at it, you see that the keys for sine, cosine, and tangent. If I were to hit the second button, let me turn this on. Second cosine is going to show me cosine to the negative 1. That's the inverse. And second tangent gives me tan to the negative 1, which is inverse tan. Okay, so do we understand what we're looking at when we talk about these things? Okay, so we've evaluated trigonomic functions for given angle measures, but here's the thing. You can also find angle measures that have given trigonomic values by using inverse trigonomic relations. What all that means is, up to this point, we've used an angle and a side to find the length of a missing side, right? If I had an angle of 30 degrees and a side that was 4, I could find out what the length of the missing side was if it was a right triangle. What we're doing today is we're taking a right triangle where we already know all the side lengths and finding the missing angle measure that goes with it. Does that make sense? Okay, maybe, maybe not, but we'll see it here in a second. Okay? All right, so if a function value, if A is a function value, then one of the inverse relations values is. So if I have sine x equals A, then then the inverse sine of A equals x. And it goes on down through there. You have a little table value or a little table setup of this on page 476 that you can look at. There's also a box, and I didn't include this in my slide notes here, on inverse trigonomic functions, their domain and range. Okay, just because we don't really work a lot with necessarily their domain and range, but they are there. So the inverse of the trigonomic functions are not functions themselves because there are many values for x for a particular value of a, meaning that we can get, as we go around the unit circle, we can find more than one place where a given scenario works, and you'll see that here as we look into some of these questions. Okay, and I think that's it for this. So we're going to move over to these notes. Does everybody have this? Yes. They did get sent out. It's important that I ask because a lot of times they don't, and that's my fault. Just want to make sure that I'm on track. All right, so for this first one, it says we want to find all possible values of the inverse sine of radical 3 over 2, and then we want to give our answer in radians. So the first thing I'm going to do is I'm going to show you how to do this on a coordinate plane so that you know what's going on, and then I'm going to come back to the same question and show you how to do it in your calculator, and I'm going to explain why your calculator is not going to give you a complete answer, okay? It's only going to give you about half the answers that exist, okay, which means that's not going to be enough on a test, okay? All right, so we've got this. I'm going to come back over and we're going to draw some of this up. So hopefully you guys have got that question sitting there in front of you. We want the inverse sine of radical 3 over 2. All right, this is what I want you to realize, is that sine is still opposite over hypotenuse, even though what we're talking about is the reciprocal, okay? Which means, from my reference angle, opposite of that angle is radical 3, okay, and the hypotenuse is 2, and I'm looking for a place where I'm getting a positive opposite, okay? Well, opposite is going to be there, right? Opposite of my reference angle, positive is going to show up there. My hypotenuse would go here. What number would go on the bottom? What do you say? Not -1, 1. All right? So does this familiar to us, this 1, radical 3, and 2? Hopefully. Do we know what this angle measure right here would be then? Not 45, not 30, although you're closer. 60. 60 goes opposite of radical 3. 30 would go up here opposite of 1. All right, so what we learn about this is that this line shows up at 60 degrees. Right? We get that? Okay. Now, here's the other thing I want you to understand, is that this also has a positive radical 3 and a 2 and a -1, but it works the same way. Notice that all we're concerned about is having a positive radical 3 over 2. Okay, do you see how I get a positive radical 3 in both reference triangles, but now I'm in a separate quadrant? All right, this is still 60, this is still 30, but what we're concerned with is at what angle does that show up? All right, well, because it's starting from here and going to there and stops 60 degrees shy of 180, it is at 120 degrees. Okay, do you follow me? Did I lose you? Everybody's with me. We understand how we got 60 and 120. Yes? Okay. So this is what we're saying, is that find all the possible values. Because it wants us to find all the possible values, is it possible that I could go all the way around and wind up right back there? Right? Our term for that is coterminal. Right? And we could go all the way around and show up here. We could go around 50 times and get back to that spot. Is that true? Okay? So in terms of degrees, what we're saying is 60 degrees plus 360 degrees times the number of times I would go around. Okay, does that make sense? And the same would be true for 120. 120 degrees plus 360 degrees times the number of times I would go around. Our problem is that it doesn't want our answer in degrees, it wants our answer in radians. So we have to convert from degrees to radians. Does anybody remember how to do that? What's that? The mode? No. This is what we do. We take our degrees and we divide it by 180, and our answer will be that fraction with pi in the numerator. Okay? So what we're going to do is we're going to take 60 and we're going to divide it by 180. What do I get? 1/3. So 60 over 180 is pi over 3. Okay? Pi over 3. I don't have to put the 1 up there because I've got the pi sitting there. So this answer is pi over 3 plus, and we're going to do the same thing with 360. We're going to take 360 and divide it by 180. Right? And get that in terms of radians. Okay, what is that? 2. So we're going to write 2 pi. All right, because we're in radians. Times the number of times I would go around. Okay, that's that part of that answer in radian form. Now we need to do it with 120. Now we know we're going to do the same thing with 360, so we'll get 2 pi times the number of times we would go around. But what is 120 divided by 180? 2/3. So what am I going to put on the top? 2 pi over 3. All right? These are my two answers, the things that I've got in brackets there. Okay, do you follow me? Hopefully. Okay. All right. Now you guys have the next question. You're looking at it, right? Okay. It says find sine, find inverse sine -1. Give your answer in both radians and degrees. Okay. Well, I'm going to go back to this first question here for a second and show you what meant earlier by the fact it wasn't going to give me all of my answers. Okay, I'm going to hit second sign, then I'm going to hit square root of 3 divided by 2. Okay, let's get my answer. Notice that it gave me 60 degrees, but did it give me 120 degrees? No, it didn't. Okay, so that's where I have to not only know what my calculator can do, but also know what I'm doing, right? That's why I showed you the picture first, because your calculator won't give you every option. How did I get 120? Let me go back. Okay, look. The original question was radical 3 over 2, where positive radical 3 has to be opposite, right? And 2 is my hypotenuse. Okay? Well, do you see how, because this is opposite and it's positive, right? We're above the x-axis, I get a positive radical 3 here as well, right? And my hypotenuse is 2, which means my adjacent is negative 1. And in this reference triangle, this is still 60 degrees because it's opposite a radical 3 in that reference triangle, correct? So what we're saying is that from our initial side all the way over to our terminal side is 120 degrees because my reference angle takes me the other 60 degrees to 180. So this is at 120, whereas here the reference angle and the terminal side are in the same place. Okay, 60 degrees is 60 degrees in quadrant 1. Okay, did that clear that up at all for you? Okay. All right, so I'm going to come back over to this other question, right, and it was inverse sine of negative 1. Okay? All right. Now, if we write this up as a fraction so that we get a ratio, we get negative 1 over 1, right? All right. So that means that opposite over hypotenuse, I'm going opposite negative 1 over 1. The problem is that we don't have any reference triangles that work like that. So I want you to go back to this, and I want you to understand that sine represents the y-axis. Okay? Sine represents the y-axis. So where am I going to be negative 1 on the y-axis? I'm going to be down here, right? Right? Is that negative 1 on the y-axis? Yes? Okay. Now, can you tell me what the degree is there? 270. 270 if we are positive, right? If we're going around. But because it's a negative 1, because we're looking for the inverse of negative 1, what we want is negative 90. We want to go around that way. Okay? And to double check, to make sure that we get this right, we're going to check our answer with our calculator. All right, so we're going to hit inverse sine, thank you. And we're going to hit negative 1. And we're going to hit enter, and notice that it shows me negative 90 degrees. Okay? Negative 90 degrees. So because we're at negative 90 degrees, that's part of my answer. The other part of the answer was we wanted our answer in radians, right? So what do I need to do with this in order to get my radian? Divide by 180. What's 90 divided by 180? What's that? Negative 1/2. Okay, so I'm going to write that as negative what over what? Over negative pi over 2. Okay, if it's just the 1 in the numerator, I don't have to write it because I know I'm going to leave my pi up there. So negative 90 degrees or negative pi over 2. Okay? How many of you feel pretty lost? Anybody? Nobody? Okay, good. Jose, a little bit. I can't tell if you're raising your finger there or... Okay. All right. Let's come over to another question. This one, this is where things get, I hate to say this, they get a little trickier even still. This says cosine theta equals radical 3 minus cosine theta. And it says for all real numbers, give your answer in degrees. This is how I want you to look at this. I'm going to try to simplify this for you. We're going to say that cosine theta equals x. Okay? I'm going to come over here. Cosine theta equals x. And because cosine theta equals x, I'm going to substitute x. We're going to say x equals radical 3 minus x. Now, if you were solving for x, what would you do here? Add x to the other side, right? So let's add x to the other side. What do I get now? No, I'm adding. 2x equals what? Radical 3. But I still want to solve for x, and I've got to do what? Divide by 2. Okay, good. All right, so you get x equals radical 3 over 2. Okay, but what does x equal? Cosine theta. All right? So we're saying cosine theta equals radical 3 over 2. What is cosine? Adjacent over hypotenuse. Okay? So let's graph that and notice that that's a positive radical 3 over 2. Cosine is your x-axis, which means that radical 3 is going to be the line that comes around along the bottom with your hypotenuse of 2. Okay? So this is going to give me a positive radical 3 here, correct? With a hypotenuse of 2 and a side opposite that's 1. All right, so what is my reference angle right here? Can anybody tell me? No, 60 goes opposite of radical 3.
45.
Huh? Not 45. 45 is 1 radical 2. 30. All right, so we're saying that this is 30 degrees. So that terminal side there is at 30 degrees. But here's what you got to remember. Okay, that's not the only place where I can get that ratio. I can also get that ratio down here. Okay, where this goes all the way around, okay, to 330 degrees. And the reason I know that is because this is 30 degrees. Okay, so it's a lot like that other question, except I'm using different quadrants. Did I lose you there? Yes? Kind of. Okay, remember, my ratio is positive radical 3 over 2. And because cosine represents the x-axis, radical 3 is just positive on the x-axis, right? So I can be above, right? I can be below, and it's not going to change the fact that because I'm to the right of the y-axis that my radical 3 remains positive. And because my hypotenuse is always positive, I could be above the x-axis or I could be below the x-axis right of the y-axis. Okay? So that means that this can be 30 degrees or I can be at 330 degrees and still get the same ratio. Do you understand me now? Okay. So because we have 30 degrees and 330 degrees, because this is 30 degrees from here to here, right? Okay, so as I go around, what I'm really checking for is where does that line stop at? Well, as I go around, it goes around, but it stops 30 degrees shy of the x-axis, which is at 360 degrees, right? Well, what's 360 minus 30? 330, right? Does that help at all? All right, so my measures for my terminal sides are at 30 degrees and 330 degrees. But because it's asking for every way in which this can be done, my answer goes back to that 30 plus 360 times the number of times I could go around, or 330 plus 360 degrees times the number of times I could go around. Where n is an integer. It has to be a whole number. Okay, so you should get B as an answer on this. Okay, I'm trying to go as slow as I can in hopes that you'll still get it. right? I don't want to lose you or leave you behind. Okay, these are tough questions. Okay? Are there any other questions about this? No? Okay. All right, and just to see your calculator do a little bit of work here, just so you know how to go back and check, is that I can hit second cosine, square root of 3 divided by 2, but it's only going to give me 30 degrees. Okay? So I need to know that I could also be below that 30 degrees, and that's equal to or equivalent to 330 degrees. So it's going to give you half of your answer. Okay? Your calculator will give you half. It won't give you the other half. Okay, let's look at another here. 4. 4's a much easier question. It gives you something that looks like this. It says here we got 36, 85 is my hypotenuse, and we got 77, and we want to know what is that angle right there. Well, we have 3 trigonomic functions that we can use. We can use all 3 because we have all our sides. Okay? So which trigonomic function do you want to use? Sine, cosine, or tangent? Just throw one out. Tangent. Somebody said tangent. All right, well, this is how we use tangent when we have all of this to find an angle measure. We're going to use inverse tangent to find the angle. Tangent is opposite over adjacent. So I'm going to do 36 over 77. So this is what I want you to do. I want you to hit second tan in that graphing calculator you've got, and inside that parentheses, I want you to put 36 divided by 77, close your parentheses, and then tell me what you get. If your calculator's in degree mode, you should be fine. So you might check the mode. What did you get? 25 degrees. Okay, 25 degrees. Now, here's the neat thing about this. Because I have all 3 sides, I don't have to use tangent. Like I said, you could have picked a different one. Cosine, right? Try out cosine. Cosine from here is going to be adjacent over hypotenuse. So 77 over 85. Anybody want to tell me what inverse cosine 77 over 85 comes out to? It comes out to 25 degrees. Okay? And then we could also use inverse sine. But I have to base it upon the angle I'm looking for. So opposite, 36 over hypotenuse, 85. What's inverse sine 36 over 85? 25 degrees. Okay? Do we understand how to do this one? Okay. So when I'm looking for a degree, I'm going to use the inverse trig function. All right, number 5. Okay, number 5, I'll read it. Don't know if I really... What time do you guys get out of here? 36? Okay. Let's see, I want to see what kind of time you're working with. 67. All right, so this is probably what I'm going to do with this lesson, is I'm going to stop probably right here, and I'm going to record with the other class the rest of these questions, and I'm going to post both videos to your classroom, okay? The homework assignment is still due tomorrow. Normally what I would do is I might have even given you a work day, but we're on kind of a time constraint to get everything in that we need to get in before your quarterfinal, okay? So you guys have got this. You'll wind up with both videos at the end of the day.